The word uranium often sparks curiosity, and sometimes even a bit of fear. It's a term people usually associate with nuclear power, atomic weapons, or even science fiction tales about dangerous radiation. But what exactly is uranium? To really understand it, we need to look closer at what this element is, how it was first discovered, and why it has become so important in both energy production and human history. Uranium is a naturally occurring chemical element found on the periodic table with the symbol U and the atomic number 92. In simple terms, that means every uranium atom contains 92 protons inside its nucleus. Because of this large number of protons, uranium ranks among the heaviest elements that occur naturally on Earth. If you were able to hold a solid piece of pure uranium metal, one thing would immediately stand out: its weight. Uranium is extremely dense. In fact, it's about 19 times heavier than the same amount of water. This remarkable density is one of the key reasons uranium holds such enormous potential as an energy source. So let's dive deeper and explore the story of uranium right here on Ordinary. The discovery of uranium itself is a fascinating chapter in scientific history. The element was first identified in 1789 by a German chemist named Martin Heinrich Klaproth. While studying a mineral called pitchblende, known today as uraninite, he realized it contained a previously unknown element. Klaproth decided to name this new element after the planet Uranus, which had only been discovered a few years earlier. At the time, however, no one understood just how significant uranium would eventually become. Throughout most of the 19th century, uranium wasn't considered especially important. Instead of powering reactors or shaping global politics, it was mainly used for decorative purposes. Uranium compounds were prized for their ability to give glass and ceramics a striking yellow-green glow, creating colorful materials that were popular in decorative art and household items. At that time, people had no understanding that uranium was radioactive. That changed in 1896, when the French physicist Henri Becquerel made a surprising discovery. While experimenting with uranium salts, he noticed that they released invisible rays capable of fogging photographic plates, even when the samples were kept in complete darkness. This unexpected observation marked the beginning of an entirely new field of science, radioactivity. The discovery was later expanded upon by pioneering scientists Marie Curie and Pierre Curie, whose research helped scientists better understand radioactive elements. Because of this breakthrough, uranium became closely linked to the development of modern physics. From a chemical perspective, uranium is a silver-gray metallic element. But what truly sets it apart isn't its appearance, it's what's happening inside its atomic nucleus. Uranium atoms are naturally unstable, meaning they can break down over time through a process known as radioactive decay. Within uranium, there are several different isotopes. The two most significant ones are uranium-238 and uranium-235. Isotopes are versions of the same element that contain the same number of protons but different numbers of neutrons. In natural uranium, about 99.3% is uranium-238, while only about 0.7% is uranium-235. Even though uranium-235 makes up only a tiny portion of natural uranium, it's incredibly important. That's because this isotope is fissile, meaning it can split apart when struck by a neutron. When that split occurs, an enormous amount of energy is released. This process is known as nuclear fission, and it forms the fundamental principle behind both nuclear power reactors and nuclear weapons. On its own, the energy produced from splitting a single uranium atom is extremely small. However, when trillions of atoms split in a chain reaction, the total energy released becomes extraordinarily powerful. When you scale that reaction up to trillions of atoms splitting at the same time, the amount of energy released becomes extraordinary. In fact, a uranium fuel pellet about the size of a fingertip can generate roughly the same amount of energy as burning a full ton of coal. That incredible efficiency is one of the main reasons uranium plays such an important role in the modern energy system. Inside nuclear power plants, uranium is formed into small pellets and placed into long metal tubes known as fuel rods. These rods are arranged in a reactor core where controlled reactions take place. As uranium atoms split, they release heat. That heat is used to boil water and produce steam, which spins turbines connected to generators, ultimately producing electricity. Because of this process, nuclear power plants can generate large amounts of electricity without burning fossil fuels. This makes uranium a key component in many countries' strategies to reduce carbon emissions and address climate change. However, nuclear energy also comes with significant challenges. One of the biggest concerns is radioactive waste, which can remain hazardous for thousands of years and must be carefully stored and managed to prevent environmental contamination. Beyond its role in energy production, uranium also has a much darker chapter in human history. During the 1940s, scientists working on the Manhattan Project discovered how uranium's fission properties could be used to build atomic weapons. In 1945, the United States dropped an atomic bomb called Little Boy atomic bomb on the city of Hiroshima in Japan. This weapon was powered by highly enriched uranium. Enrichment is the process of increasing the concentration of uranium-235 within uranium, making it more suitable for use in nuclear reactors, or, in some cases, nuclear weapons. The development of uranium-based weapons dramatically reshaped global politics and military strategy. Almost overnight, uranium transformed from a little-known element into a symbol of immense destructive power. Since that moment, uranium has remained at the center of global discussions about nuclear proliferation, energy security, and international stability. Another key part of uranium's story is how it's mined and processed. Uranium naturally exists in a variety of minerals within the Earth's crust, and large deposits have been discovered in several parts of the world. Major uranium-producing countries include Canada, Australia, Kazakhstan, and Namibia. The process begins by mining uranium ore from underground or open-pit mines. Once the ore is extracted, it goes through a series of chemical treatments that transform it into a concentrated powder commonly known as yellow cake. This material is then refined further and often converted into uranium dioxide, which is used to produce fuel for nuclear reactors. If required, the material can also undergo enrichment to increase the proportion of uranium-235. However, uranium mining comes with serious environmental and safety considerations. Mining operations can potentially contaminate nearby water sources, and workers may face risks from radiation exposure if strict precautions are not followed. Because of these concerns, the uranium industry operates under careful safety standards and environmental regulations. Even with these challenges, uranium extraction continues around the world because of its critical importance to modern nuclear technology. Health and safety are always central topics when discussing uranium. In its natural state, uranium is only weakly radioactive. In fact, it often presents more of a chemical toxicity risk than a radiation hazard. Handling small amounts typically does not cause immediate harm. That said, problems can arise if uranium dust is inhaled or if someone is exposed to high levels of radiation produced by uranium's decay products. For this reason, strict safety procedures are enforced throughout the nuclear industry to protect workers and the environment. Another interesting aspect involves depleted uranium, which is the material left behind after the enrichment process removes much of the uranium-235. Because depleted uranium is extremely dense, it has been used in certain military technologies, including armor-piercing ammunition. The use of depleted uranium in warfare has led to ongoing debates about its potential health and environmental effects, making it a controversial subject in discussions about modern military technology. Uranium is far more than just another entry on the periodic table. Over time, it has become a powerful symbol of both human achievement and human caution. This single metal has played a role in some of our greatest technological advances, while also reminding us of the immense responsibility that comes with such power. In many ways, uranium represents two sides of the same story. On one hand, it offers the potential to generate enormous amounts of energy and help power the modern world. On the other, it has also been linked to some of the most destructive technologies ever created. As the world continues searching for cleaner and more sustainable sources of energy, uranium will likely remain an important part of that discussion. It's an element that constantly challenges humanity to balance innovation, safety, and responsibility. Thanks for watching. If you have ideas or suggestions for future videos, feel free to leave them in the comments. We'd love to hear from you. And if you enjoyed this video, don't forget to like, subscribe, and stay tuned for more fascinating stories hidden within the everyday things around us.